Friday is spring break, and so we won't have any class on Friday of this week. And on Monday is when your demand estimation calculations are due. And so that should be submitted to Blackboard before 1 o'clock. And you need to follow that template file that I provide on Blackboard. You know, the assignment description includes one of the pages is the format, and you can hand fill that in. It doesn't need to be like you reconstructing that same spreadsheet in Excel. I'm perfectly content for this phase 1 submission to include just hand calculations. That's fine. And of course, one of the things that you can do to improve the quality of your estimates is do specific research. That's not March 6th. That's very strange. Do specific research that are for the city that you've been assigned. And so, for instance, if your assigned city is Phoenix, Arizona, then probably your demand estimation is going to be very different than somebody who lives in Columbus, Ohio, because of the availability of water and the pricing and the sorts of things that people do for landscaping. So in your initial submission on Monday of next week, you should include the supporting documentation and just a summary of what outside research you've done to inform the calculations that you're performing. Homework 8 is posted on Blackboard now, and that is going to be due on Friday the 26th of March. We're going to be continuing with Chapter 11 today, which is where we delve into some of the issues related to Manning's equation. And so far we've been looking at Manning's equation mostly for engineered channels rather than those that are just natural or that have formed over time to convey water. But here's a picture of a channel that's experienced quite a lot of scour and erosion. And one of the ways that we can use Manning's equation is in conjunction with the equation that defines shear stress. And if you do a geotechnical analysis, or maybe you understand the characteristics of the stream, and you have tables of data that describe what allowable shear stress is to prevent scour, then, so if you know the shear stress and the slope of the channel, then you can use this equation to solve for a hydraulic radius. And usually when we're applying this equation, hydraulic radius has a physical meaning. You know, hydraulic radius is the area divided by the wetted perimeter. But if you know the shear stress and the slope, then the hydraulic radius isn't so much a physical parameter as just an abstract value that then you would substitute into the Manning's equation. So you would solve for the hydraulic radius here, and then substitute that hydraulic radius into Manning's equation to tell you what is the velocity that is going to cause that shear stress. So the question may sometimes be, how fast can the water move through a channel and not cause additional damage? You know, if you have a cohesive soil, then you want to limit the velocity of the flow so that it's not carrying particles downstream. Because when the water's moving too fast, you can sometimes even see it in the river. We live right next here to the Ohio River, and when it's been really rainy, flash floods, the river turns brown because it's carrying sediment for all of the streams, the tributaries. But when it's relatively dry weather, or if it's wet but not flashy, if it's just kind of a steady rain and it's not scouring the channels quite as much, then the water doesn't look that chocolate brown color that you'd associate with scour. So just to get some practice with this idea of permissible tractive force, which is related to the shear stress that you can apply to a natural surface and not induce scour. Let's say that we know that shear stress that can be allowed. If we have a situation where the maximum shear stress would be 10 newtons per square meter, and we know the slope of a channel, in this case 1.5%, and we know that it's natural earth, straight, good condition. So that would be a description you could look up out of a table of N values. And so natural earth, and it doesn't tell us specifically what kind of soil, but we do know a little bit more about its specific characteristics because they've taken a sample of it into the lab and estimated what the shear stress is. But let's just, with this description of natural earth, straight, good condition, let's infer from that an n value that applies. And so here, the procedure that you should follow is solve for a hydraulic radius, and then substitute that hydraulic radius into Manning's equation and solve for the velocity. I'll put you into the breakout rooms for just a moment and give you a chance to find out how fast can the water move through this channel to avoid scour. Let's take a look at the solution for this one. Okay, so starting with the shear stress and the unit weight of water, 9810 newtons per meter cubed, and the slope is unitless. And so what we end up with is units of length, and you should have 0.0680 meters. And this never told us anything about what the channel actually looks like. It didn't tell us if this is a trapezoidal or rectangular or irregular. It didn't say what's the depth or any of those characteristics, but we know that, and I guess part of the reason why it doesn't matter is it doesn't matter how wide the channel is or how deep it is, because the critical point is going to be at the boundary of the water and the soil. So it doesn't matter how much depth is above that, but it's down low where the water is applying the force to the soil and trying to dislodge it and start to transport that sediment downstream. And so this hydraulic radius doesn't have a physical significance here. We don't know the area or the wetted perimeter, but it's really more of just a placeholder that we can put into Manning's equation and then get the maximum allowable velocity. So just over 1 meter per second. Okay. Now, velocity varies as a function of depth, and we've previously talked about velocity profiles, and you can physically measure that. Here's an instrument that has a little impeller on the inside of it, and so the way that that would be used is you could dip it down into a stream, and assuming that your boat is not moving, so maybe you'd want to be holding on to some sort of a anchor or a tether that's connected to the shore of a river. So assuming that you are motionless, then the water is flowing past, and then there are going to be some losses as the water is going over that impeller. So this will have been previously calibrated so that they're converting a certain number of revolutions per minute on this device into a flow velocity. And then if you wanted to, you could dip it deeper or shallower and get an idea of how the velocity is changing through the profile. And there are some numerical ways to estimate velocity as a function of depth, and our textbook addresses some of those. If you graph those functions, their main feature, like this one that's based on the von Karman constant, this equation, its main feature is that it has the shape that we sort of know is true for open channel flow, where the velocity is approximately 0 at the interface of the water and the soil, but then the further away you go, then it's increasing in a positive direction, and the reason for that is that as you get further up and away from the bottom boundary, there's less shear stress that is being applied by the water to the soil and vice versa. And so here, y is the distance from the bottom of the channel. So it's how far up you are from the bottom of the channel, where d is the overall distance of the depth. And then slope is a key feature in this equation, and the steeper the slope, the faster the velocities are going to be, and then there would also be more of a difference between the velocity at the surface compared to the velocity at the bottom. So that's really, if you look at the vertical axis of this representation, that is what this means is that you can know kind of the average velocity, which you get from q divided by area. But if you know if you want to know the velocity at a certain location, how far from the bottom of the channel you are, then you can use this as a means of estimating that. And there are simpler approaches. Over time, it's been observed that you could just go 4/10 of the way down from the bottom of the channel, and that the average velocity is about the velocity at that specific location, or that the average velocity, if you averaged the velocity 20% down and 20% from the bottom, then that's a pretty typical representation of the velocity on average. If you're taking the point velocity, we sometimes want to know the average, and then vice versa. If you have the average velocity and you want to know the velocity at a point, then this is the equation that you'd use for that. I told you about a video that I made recently. Let me see if I can pull that up and show you the flooding of the Ohio River. Okay, it's coming up now. We'll have to suffer through a bit of a delay. Okay, so this is a video I took, I guess it's now been 2 weeks ago. It was March 3rd. That was a Wednesday, right? That was the day that the water was peaking. And my computer's being a bit laggy. I may have too many things open right now. Let me just switch from 4K to a lower resolution. That'll probably make it a little bit more smooth. All right, so the point that I want to make in showing this to you is consider all of the debris on the edges of the floodplain. The water is moving very swiftly through the center of the channel where there's no obstructions and where the flow depth is greater. So at this location in the center of the river, I think the flow depth is probably more than 40 feet. The flood stage that we were at 2 weeks ago on Wednesday, the depth is, they say it's like 50-something feet, but I'm not sure what the datum of that is. I don't know if it's the bottom of the channel or a historical channel bottom, because there's always sediment moving in and out. So it could be that the actual physical bottom of the channel is above or below that previous datum. But I mean, let's just assume that it's approximately 40 to 50 feet. And so in the center of the channel, the water at the surface has very little resistance because it's far from the edges, and those edge effects are where resistance is applied, and it's far from the bottom. So the water is moving swiftly through the center of the channel, but moving very slowly because of all the debris. Let me play this again. So whether it's playground equipment or flagpoles or trees, park benches, trash cans, restroom buildings, all of those things are reducing the speed that water can flow. All right, so I think you get the point. Now, what we can do is apply techniques to come up with a numerical weighted average of Manning's N. Remember, the N value is the roughness, and the floodplains will have a very high N value because there's lots of resistance there, and the side slopes and the main channel will have a much lower N value where there's less resistance to flow, both because it's a smoother surface and also because the flow depth is greater. And so our textbook introduced a couple of different ways for you to come up with a weighted average N value. And the Horton-Einstein method is one of those approaches, and what it suggests is that what you can do is if you know an N value for a lot of different surfaces, then you can come up with a perimeter weighted average. So that's what this is it's a perimeter weighted average. Rather than being just a simple average, which would be silly, right? Because it wouldn't take into account the relative size of everything if you just did a simple average. Or if it was area weighted, that may not also make the most sense, because resistance depends on perimeter. You know, the resistance is applied by the surface, not by the area. So I think the Horton-Einstein method is probably the best approach introduced by our book to come up with a composite N value, composite roughness. So I wanted to point that out to you. Now, here is Manning's equation solving for flow rate Q. Earlier today I showed you the velocity version of that, but to get it from velocity to flow rate, we simply multiply it by cross-sectional area. And since cross-sectional area was already in the hydraulic radius term, you know, r to the 2/3 power, what r is area divided by wetted perimeter. So we have area to the 1 power and area to the 2/3 power, and so that's where we come up with this expression of area to the 5/3 power that we used in some of our previous problem solving. So that's in the numerator, and then wetted perimeter to the 2/3. So here's Manning's equation. And let's say that we have a variety of different channel profiles, but we want to maximize flow rate. So think about, if you have some constant area, a constant N value, because regardless of what the shape of the channel is, we're going to go for the same area, the same roughness, and the same slope. We're just going to change the configuration. So we could have one channel that's narrow but deep, or another channel that is wide but shallow, and then a couple of channels that are in the middle. You know, one that's 5 meters wide and 4 meters deep, and vice versa. So think about, in this equation, if slope is a constant, N is a constant, and area is a constant, how do you get the biggest Q possible? Well, the only other variable that we haven't talked about yet is P. And so the way that you'd get a big flow rate is by minimizing perimeter. Smallest perimeter. That's right, Gavin. Now let's take a look at, what if we just set this up on a spreadsheet as a proof? Let's solve Manning's equation for a couple of different shapes. So let's set it up. We've got a rectangular channel, and I'll define here the slope is 0.0. Do I have an example slope here? All right, 0.01 and an N value of 0.03. So slope of 0.01 and then an N value, N value is 0.013. And I want to play around with a variety of different bottom widths, different flow depths Y, and then from those I'll calculate the area, wetted perimeter, hydraulic radius, and then therefore the flow rate in cubic meters per second. All right, so does everybody understand what I'm going to be doing here as the setup is I just want to compare and see if that's really the case. If I put it into Manning's equation, what is the flow rate for these 4 different options? You know, how can we maximize conveyance through a channel? Because as a hydraulic designer, that's often what you want to do, is you want to get the most flow through a channel with the least amount of excavation, because excavation is what costs money. In the same way that in closed channel hydraulic design, we're trying to minimize the size of the pipe that we use, because pipe is expensive. In open channel flow, the thing that we want to minimize is the cost of the land of a channel, and then also the cost of excavating that channel. All right, so we had, this first one has a width of 2 meters. The next one has a width of 10 meters, a width of 5 and 4. Okay, our depths were 10 meters, 2, 4, and 5. And I guess it would be incomplete if I don't define my units here, so I got to set a good example for you. You should, if you're doing calculations, always include the units along with them. Area is going to be units of meters squared, of course. Wetted perimeter will just be units of meters. And then hydraulic radius would be units of meters. All right, so our area since it's rectangular, it's easy. Bottom width multiplied by the depth. So all of them are going to have this same 20 meter cross-sectional area. If you multiply the width and the depth, they're all 20, but the wetted perimeters won't be the same, will they? So for a rectangular channel, wetted perimeter is the bottom width plus 2 times y, because you've got the side effects and then the bottom. So bottom width plus 2 times y gives us 22 meters of wetted perimeter for this one. It's lots of wetted perimeter because it's so narrow and deep. Think about excavating this. It would be tricky from just kind of a feasibility standpoint, but for it to be vertical like this, you're going to have to put in a concrete lining for it to maintain that profile. Otherwise it would collapse in on itself. That's going to be costly to line it. Let's spread this formula down through subsequent rows. So this is our one that has the least wetted perimeter. So let's see if that is the one that gives us the most flow rate. Hydraulic radius is area divided by wetted perimeter. Okay, so we have different hydraulic radius for all of these, and now I'm going to do Manning's equation. So Q is area to the 5/3 power. So here's area to the power of 5/3 slope times slope to the power of 0.5 divided by n times wetted perimeter to the power of 2/3, 0.6667. Okay, so I think that's going to give me the flow rate, yeah. And the flow rates, the highest flow rate corresponds to the one with the least wetted perimeter. So highest flow rate from minimizing wetted perimeter. Perimeter. Let's just assume that that's spelled correctly. I hope it is. Any questions or comments about that illustration? What if it was 5 by 5? Well, then it wouldn't have an area of 20. I mean, it would, I think it's going to give us a much better flow. Yeah, 270. But the key thing about all of these examples was, let's just assume that we are going to be excavating 20 square meters. So how does the shape affect the flow conveyance for a certain cross-sectional area? Good question. All right. So here are wetted perimeters, and the best one was the one that was the flow rate with the least wetted perimeter. And so that most efficient cross-section here is the 4 by 5, but the most efficient cross-section for a trapezoidal channel, we have in our textbook a variety of equations that tell us like the optimal shape. So the optimal shape of a trapezoidal channel is one where, if based on the depth, then the bottom width is a function of some depth y, and it's a relatively steep side slope. So square root of 3 divided by 3, that's going to be less than 1. So it's a pretty steep side slope, because a 1-to-1 side slope is already by itself pretty steep, but this is steeper than that because root 3 divided by 3 is 0.577. So it's less than 1 unit of horizontal for each unit vertical. So this is the best trapezoidal channel. And it happens to be the trapezoid that almost accommodates a half circle. So the contact points would be halfway on the side slope here. That's where you would have a contact point with the half circle. And same thing at the bottom there. Hydraulic radius, if you have area divided by wetted perimeter, it's just the depth divided by 2. So the other most efficient channel shapes are defined in the textbook. For a trapezoidal channel, for a rectangular channel, the most efficient one is a half square. For a triangular channel, it's also a half square, but it's just turned on its side. Semicircle and parabola. So here's that triangular channel. It's the one that most nearly accommodates a half circle. Okay, so what would be the flow depth in the best triangular channel for a flow rate of 2.5 cubic meters per second, Manning's N of 0.013, and a slope of 0.01? So what we would do here is we would say Q is 2.5, N is 0.013, and then we would substitute in the expression for wetted perimeter. Since this is a triangle, you'd instead of P, you'd have 2.83y in the P value, and instead of A, you just put in y squared. And let me just show you, rather than having you crunch the numbers on these. I think it is. Best triangle. Here we go. So we substitute in to Manning's equation our geometric parameters as a function of the depth. And so the flow depth here for the best triangle would be 0.851, because if we put it into a solver, and the y exists both in the numerator and the denominator because the area is a function of the flow depth and the wetted perimeter is a function of the flow depth, so we get 0.851 meters just once we go through the solver there. All right, now I saved us about 15 minutes of time because I want to get just one more in-class attempt at solving Manning's equation with the trapezoidal channel. And this is something I said that you absolutely, positively have to be able to do. And this semester you have kind of the added bonus of, if you choose to do it with a spreadsheet rather than figuring out how to use your solver, then that's okay, but I still think it's really a good idea for you to learn how to use the solver on your calculator. We know that this channel has a bottom width of 2 meters. We don't know the flow depth, and this is saying find the normal flow depth. And remember, what normal means is we assume steady, uniform flow, and that's the assumption that has to apply in order for Manning's equation to predict what the depth is going to be. Because if you don't have steady uniform flow, Manning's equation isn't going to be able to tell you what the depth is. So if the flow rate is changing over time, or if the water velocity or depth is changing in the direction of flow, so if you have non-uniform flow because the water is approaching a change in slope or some sort of an obstruction, then we'll have other techniques that we learn later on to predict what the flow depth is in those situations. But here we're assuming steady uniform flow, and so we just want to know what would be the flow depth assuming no perturbances to the flow. And so we rearrange Manning's equation, area to the 5/3, slope to the 1/2, divided by n times wetted perimeter to the 2/3. And here are the geometric formulas for a trapezoidal channel. Here the flow rate is 21 cubic meters per second, and I'm saying that we have a 1-to-1 side slope. And so T, the parameter T, that is the horizontal component of our side slope, is just 1. Okay, as before, I'll put you into those breakout groups and I'll be going between them, but I want to see if you're there yet. Have you got to the point where you're able to find the unknown flow depth in a trapezoidal channel? Once it's non-functional. So I just ended the breakout groups a little bit early. I'm wondering, has anybody found the flow depth yet? Have you got to that point where you've actually solved for y sub n? I'll give you a few more moments then. Caleb, that's awfully close. My guess is probably you got it right. It may just be a slight round-off issue. I'll let you continue calculating for a few more minutes, then I'll show you my solution. I've got the solution up on the screen in case you want to check some of your intermediate steps along the way. So now remember, if we don't want to use a solver in a calculator, the way that we can solve this with Excel is we want the left-hand side equal to the right-hand side. So here I've defined what's the area, the wetted perimeter, and so on. Let's see if I can just translate that into an Excel spreadsheet solution. If some of you did that, it may be the way that you're approaching things. All right, so we have some guess value of the depth. Maybe it is, maybe starting off as a guess, my depth would be 1 meter. Okay. And flow rate, cubic meters per second. And I'm going to have the n value and the slope, and then the area and the wetted perimeter. Okay, so the flow rate here was 21 cubic meters per second. Our n value is 0.035. The slope is 0.0075. The area here off of the formula b times t, b plus t times y. So let me also here define the side slope just so that I don't have to type that in, and I could adjust it if I wanted to. T, which is the side slope and will be unitless, and then b, bottom channel width in meters. The bottom width is 2 meters and the side slope, it's 1 to 1. Okay, so now our expression for area is going to be the bottom width plus t times the depth guess, and then all of that is times the depth guess. Okay, so if it is 1 meter in depth, then the area would be 3. Now the wetted perimeter, I need to have this intermediate term W. So let me also define here W. And the way that we do that is it is 1 plus T, oops, 1 plus T squared to the power of 0.5. All right, so now wetted perimeter is going to be the bottom width of 2 in this case, plus 2 times y times W. All right, now what we're going for is we are going to find the right-hand side and the left-hand side. And so the, maybe I should have left-hand side on the left, right? Oh. Okay, so the left-hand side, Q times N divided by slope to the 1/2 power. So Q times N divided by the slope to the power of 0.5. So that's our left-hand side, and our right-hand side is going to be the area to the power of 5/3 divided by the wetted perimeter to the power of 2/3. Now, the two don't equal right now. I need to have a difference cell that goes down to 0. And so now in goal seek, what I'm going to do, data, what if analysis, goal seek, my objective is I want the difference to be 0 by changing the depth. And it goes through 2.03. So I probably rounded off too aggressively here when I was calculating my left-hand side, because 2.03, that's the value that Caleb got as well. Well, okay, that is probably the last trapezoidal Manning's equation normal depth practice that we're going to get during class, but I think you've got some on your homework, so I'd encourage you to get started on that. Remember, the top priority is this design project phase 1 submission on Monday. We don't have class on Friday, but I'll be responsive to your emails. If you have any questions, just let me know. That's it for today, everybody. Take care, and I hope you have a nice spring break.